Now, Mr. Ferran Castro, in the consortium of 8 organizations, 4 of them were Catalan. We have people from Xarxa Oberta, from anything having to do with fiber optics. We had UPC, CCA UPC, they are coming later, and Ferran Castro from ZIV, former DMAT, and currently I don't know the name anymore, because this is one of these companies which is staying, but the name is changing. So please, the floor is yours. With him, the challenge was about distances. Up to. We were lucky. At this point, we were very optimistic at the beginning. And our first proposal said that we would reach 15 kilometers distance with a PLC. And it was then the project officer who said, please write down up to. And this saved our life.
Thank you. You hear me? So thank you for being here. Thank you to Stavanel for giving us the opportunity of sharing all our knowledge with you. My responsibility in the project was communications, and I will show you a nice picture. This is Google Earth, actually. This is by Fogona de Ripollès. So we have the different substations, Bergerno, Planallonga, Piella, and Artigas. So our purpose in the project was to build a communications network to give support to the IDPR. I mean, communications are never a goal in itself. We pay a service to the telecontrol system. So the question is, do we really need another PLC? Are you sure about that? So let's have a look at the current state of the art. This was an interesting overhead that we showed in Brussels in the beginning of the project. If I draw transmission time and geographical distance, then it happens that I have the early PLC systems dated 20 years ago were intended for high-speed internet access, so providing internet access to the home. At that time, the idea was to reach 45 megabits per second, which was notorious. We are talking 20 years ago. 45 megabits per second 20 years ago. That was really challenging at very short distances because they had to cover the distance from the secondary substation to the home. That's hundreds of meters. Then, today we also have PLC for smart metering system. PLC for smart metering means transmission capacity is relatively low. We don't need any more than, let's say, 100 kilobits per second, order of magnitude. And the distance is, again, from the secondary substation to the home, to the meter, in fact. So we are talking about hundreds of meters. We also have PLC for in-home applications. So believe it or not, you have your computer in the dining room, and you have the printer in your sleeping room, and you can communicate them over the mains. So the wiring at home becomes a local area network, and for this, it is said that you need 1 gigabit per second, but at least the house where I live is relatively small. It's only 20 meters from one side to the other. And then we have PLC for energy management. This is one of the technologies which is being taken into account for the electric vehicle. We talked about electric vehicle this morning. It's 1 megabit and again short distances. Now, the rural environment means I need to cover long distances. I'm not talking about hundreds of meters. I'm talking about some kilometers. We focused our mind on 15 kilometers at the beginning of the project. We had some nice discussions with the project officer. She said, don't be so strict with yourself. Just say up to 15 kilometers. So we decided that we would need a PLC system covering this distance, and since we are talking about rural environments, the amount of information is relatively low. I'm going to give you some numbers about the amount of information. So this is why we focused our ideas on new PLC design. Now, this overhead has been borrowed from my colleagues of the UPC. These overheads actually describe the operation of the IDPR. The IDPR is the star of the project. I have to provide communications service to the IDPR. So the customer is always right. Let's look at the customer. And this is what the customer needs. Customer needs this exchange of messages without set points. My colleague Volker has just talked about set points. This with set points, so this exchange of messages, these sizes, and in these periods of time. So if we take the hassle to go over all possibilities, then the conclusion is the worst case is the IDPR will need a message of 512 bits in 10 milliseconds. That is the worst case. And that leads us to 51 kilobits per second. But if you remember Ramon's overheads this morning, the IDPR is connected to an RTU that encapsulates all these messages into a 104 protocol. So we encapsulate this in a 104 protocol, which means TCP and IP, and also looks like a nice idea to prepare the system for the cybersecurity world. It's a fashionable subject these days. So this, if I add this 512 bits, I add the TCP and the IP security, then that leads to a requirement of 166 kilobits per second. And now, we go back to the previous overhead, and you will see, yes, there are 1, 2, 3, 4 substations in Vallfogona. So we thought, in the worst case, we might be able to handle up to 4 IDPRs. So we desired a concurrency factor of 4. So if this is valid for 1 IDPR, then this is valid for 4 IDPRs. So to sum up, the specifications for the project are 600 kilobits per second in 15 kilometers until the very first meeting with the project officer. Then the specification became up to 600 kilobits per second up to 15 kilometers. Now, don't get scared about this. There's no exam today, no problem. Now, is this technically feasible? Can I transmit these kilobits per second over such a distance? And the answer is Shannon's limit. Shannon, in 1948, he wrote his PhD thesis. It's only 3 pages, and he proved this expression. This expression gives you the maximum transmission rate that can be attained over a given communications channel. And the nice thing is that Shannon was not an engineer, he was a mathematician. So his conclusion is independent from the technology. It is valid for PLC, it is valid for radio, Ethernet, fiber optics. And in, let's say, 1,000 years' time, fiber optics will be obsolete, will be using human telepathy, but Shannon's limit will still be valid. So, we have to compute for this expression that is transmit power, this is a spectral distortion, this is noise. When the channel is flat, this expression can be simplified to this one, and the nice thing is that if we look at these 3 pages, we shall realize that this is only valid when there's an infinite decoding delay, which means the system is not useful in practical terms. So if you want to get very close to this limit, you must be able to accept an infinite decoding delay, which is not practical. So, can I transmit up to 600 kilobits per second in up to 15 kilometers? Let's have a look at this expression. So, preliminary measurements, we went to Bifogona. This is, for example, I put a transmitter at El Verger, I receive at Planayonga, Piella, and Artigues, and I look at the channel distortion. Then this is the signal-to-noise ratio at Verger, and then I perform numerical calculations, and that is the conclusion. The conclusion is that in the very worst case, I can achieve up to 2.3 megabits per second. So, channel capacity is higher than I need. 2.3 megabits per second is higher than 600 kilobits per second. That's clearly a green light for the project. So we started the project. First step, laboratory work, simulations. We chose two different approaches, multi-carrier modulations and spread spectrum modulations. So we performed some signal processing simulations with mathematical models. That's a simulation of the spread spectrum transmitter. Sorry. That's a simulation of the spread spectrum receiver. If you are familiar with spread spectrum technology, you will notice these are the detection peaks at the receiver. Just as a curiosity, this modulation is being used in all communications systems that focus on robustness, like, for example, GPS or the Internet of Things. Then we simulated the multi-carrier approach with 256 subcarriers. And then we built the prototype. Once we had a green light from the theory and the simulations were successful, we built the prototype. It's basically one board. You can see here the power amplifier, signal processing with all the CPUs and the modulation and demodulation algorithms, power supply, which is more difficult than it seems. Then we have the Ethernet, the communications port, and so on. Rural project means you have the opportunity of having a nice day in the sun, even if you're working, but you're also in a beautiful landscape. So these are the results, but these are real results in real distribution lines, rural lines. So we tested from short distances to long distances. So we tested a very broad scope of possibilities. For example, short distances. By short distances, we mean some hundreds of meters, from 200 meters to 500 meters. So the first results were very surprising, and it is the fact that the upper part of the frequency spectrum exhibits better propagation characteristics than the lower part of the frequency spectrum. Just the opposite of the urban environment. All PLC systems designed so far are focused for the urban environment. In the rural environment, the behavior is different. When the project started, I was so happy thinking about rural environments. I said to myself, no interferences at all. I mean, we are surrounded by cows, literally speaking, and cows don't browse the internet. So I felt very optimistic about that. I didn't know that cows don't browse the internet, but cows have electric fences around them. You can't imagine how high the level of interference was in the rural environment. It's unbelievable. And these pictures taken by Ramon, this shows what happens when the power supply to the customers is interrupted, no electric fence, and this is what we get when we have the electric fence turned on. So that is something we have to live with. I mean, real operating conditions is supplying electricity to the customer. So that's what we got. Actually, this shows the frequency response of the channel, and the blue plot, not so easily to see, but the blue plot shows the desired signal plus the interference. So we were successful at distances of 8 kilometers and transmission rates of 320 kilobits per second. I must admit that the following test was not so lucky. The following test was 10 kilometers, and we didn't get any signal at all, transmitting here and receiving here. And it seems that there were no interferences here, but it seems that the reason is we had many lines connected in parallel, T of what we call in the electric environment. So it's like having a pipe of water with holes. You lose the water. So it's like losing the transmit power in the lines that are connected in parallel. There's not much you can do about that. There's not much you can do about that. If there's no signal, doesn't matter whether the signal is robust or not. Then we tested 12 kilometers, and again, we came with very nice interfering levels here. Transmission, we must admit, transmission was not successful. So, as a summary, of the different distances that we achieved, 8 kilometers seems to be the maximum, at least in the rural environment, at least with the technology we have developed so far. At 8 kilometers is, let's make a technical joke, it's only 3 dB from what we expected. It's half the value, and that's only 3 dB from what we expected. And other differences of this PLC system, when you test, for example, PLC for smart metering, then you have a building with many neighbors, and each neighbor has a smart meters, and then all PLC systems transporting the information of the smart meter must be able to coexist. But they all cover more or less the same geographical distance. Now, in Baifogona, this is clearly different. We have Berger, then we have Planayonga, Piella, then we have Artigas. The distances are long, so the distances are different. Now, what happens if one of those signals are interfered? And here we borrowed some concepts from the Internet of Things world. The Internet of Things, one of the highlights is that every system can behave as a transmitter, as a receiver, and also as a relay station for the others. So, perhaps today I'm not a person, I'm a PLC actually. I'm transmitting to another PLC. If tomorrow channel changes and the attenuation is too high, then I will ask another PLC to do a favor for me. I transmit my information to a different PLC, and then he behaves as a relay station to other systems. So that's what we call the MAC layer, and these are the results of the field test of the MAC layer with one PLC system behaving as a relay station for another two. And of course, transmission rate has to be adapted over time, because the level of noise changes. I mean, by Shannon, if you remember the expression, we had noise power at the denominator, but if that changes, then Shannon's limit changes. So we must be prepared to adapt the transmission rate just in case the channel noise changes, which may happen if a customer, for example, turns his computer on, like Volker said, or a photovoltaic cell begins working, difference from day to night, or so on. This is one of the most, it is not the longest line, but it was certainly one of the most difficult lines, because there's a transition from overhead to underground, which means the channel impedance changes, so we get like a reflected power. I mean, for example, this is air, that is the wall. If I throw a tennis ball to the wall, then the tennis ball will come back to me because of the difference. So same happens in telecommunications. When we have an underground to overhead transition, then a very important part of the transmitted power comes back to the transmitter. So these type of lines are very challenging, and we got 1.5 megabits per second sustained. So, as a summary, we can say that with the new PLC system we have developed, we can reach up to 8 kilometers, which is not what we expected. We expected 15, but in any case, that's much better than the previous state of the art, which was hundreds of meters, at transmission rates that are well enough for the operation of the IDPR. So the figures outperform the state of the art at the beginning of the project, and we consider that the PLC system is perfectly able to support the operation of the IDPR. During the lunch, I got a question about PLC and internal latency. Internal latency in this system is 4 to 6 milliseconds. If you remember Shannon's limit, I said that the closer to Shannon, the longer the delay. Is that important for your application? I mean, if you're browsing the internet, 10 milliseconds are not important. But if you are telecontrolling energy, 10 milliseconds may be very important. So that's something you must bear in mind. I mean, when you go home tonight and you browse the internet and you read the newspaper, for example, you will not notice whether the internal delay is 10 milliseconds or 100 milliseconds. Actually, in ADSL, it can be as high as 100 or 200 milliseconds. So this system is intended for the transmission of telecontrol signals. That is why we want to keep the transmission rate as low as necessary, not higher than necessary, to avoid increasing this number. So, any question on the PLC now or later? I'll be glad to answer. Thank you.